break time, mental break. So just for fun, let us say that we have a Sardarji, but it could be you or me or anybody, as I said. So this young Sardarji is driving a car and the police stops him. Now he is seriously worried. But the police stop him, pull him on one side, and they look everywhere inside the car and they say that, sir, you should be very happy. Congratulations to you. This is our traffic week. You have won a prize of $100. Oh, he suddenly becomes very happy and he said, okay, please, yes, very nice. How? He said, you see, you are wearing a seat belt and this appears to be your father beside you. Most probably he is also wearing a seat belt, and the lady behind appears to be your mother. She is also wearing a seat belt. So this is very good that everybody is safety conscious. So we are randomly giving some prizes to encourage the people and the public and so on. So he is very happy and so on. He said, okay, now give me your names and details and so on. So we will mail you $100 check. During that, he is just talking. So he said, sir, by the way, what is your name? He said, I am Banta Singh. So, oh, yes, okay, Mr. Banta Singh. Just, I am writing this, all the details and so on. But just out of curiosity, when you get the $100, what will you do? Banta Singh says, immediately after getting, I will go to the traffic police office and get a new license and pay its fees. Don't laugh. The mother is sitting behind. She says, officer, don't believe him. He is a total liar. 2 weeks ago, I gave him the money to go and get the license done, but he went to the bar, to the pub, and he drank all the money. So he will not get the license. He will use this money to go and drink. Don't laugh. In the meanwhile, because of all this talk, the father was half asleep. He was nodding, but he got up and they saw that, oh, we are stopped and the police is there. So he starts shouting at Banta Singh, Banta, I told you this is a very bad idea. We should not go out and drive around the city in a stolen car. Now you can laugh. Okay, so this was your problem. So when you write the knowns and the unknowns, tensile and compressive stress of 120 and 30 megapascal, right? So 120 megapascal is plus, 30 megapascal is minus. This is very critical how you read it. Tensile and compressive. So 120 megapascal is a plus load stress and 30 megapascal compressive is a minus. Okay. And then this is the yield strength, of course, and this is the fracture toughness. That is okay. It is an edge crack. So the length of the crack is not 2A, it is A, and that A is 1 millimeter. The equation is given, dA dN is equal to this delta K raised to 3, right? So what is the equation? dA dN is equal to A delta K raised to M. So a small m is 3. A small m is 3. And capital A is 2 into 10 raised to minus 12. Assume y is equal to 1. What is the unknown? How many fatigue cycles? So NF is unknown and all these other things are given. All these other things are given. Okay. You go back to the NF equation. NF. AF raised to 1 minus m by 2 minus A naught raised to 1 minus m by 2 upon A raised to something, Y raised to something, delta sigma raised to something, and so on. What is the delta sigma here? What is the delta sigma here? What is the maximum stress? 120 megapascal. Minimum minus 30. So 120 minus 30. Right? The signs are very, very critical. So delta sigma. Anything else? Anything else? In the NF equation, A naught is given. A naught is given. Right? A naught is given. capital A is from the equation, small m is here, y is given, delta sigma you find out. What is still there? Unknown. AF. Yes, AF is there. So you have to find NF, that is already the unknown. And AF, the crack size, final crack size at which it will become critical, is also unknown. So what will you do? What will you do? You have to first find AF and then put into the equation, isn't it? So you are thinking there are only 3-4 equations. What is your basic equation? K1 is equal to y sigma root pi A. Yes, y sigma root pi A. From there, if you make K1 as K1C, of course, remember, don't use sigma, right? Which sigma? You see, in the K1 equation, when does it become critical? When does K1 become K1C? When sigma becomes sigma F and A becomes AF. Remember that, right? K1 is equal to y sigma root pi A. K1 will become K1C, the fracture toughness of the material, if sigma becomes sigma F and if A becomes A critical. So A critical will be the unknown in this equation, you will find out. What will be sigma critical? The maximum load. Remember, it is not the delta sigma in this equation. The load, when it is at its maximum value, will cause the crack to become the critical crack. So use the K1 equation where K1 becomes your K1C, it is given in the problem, and your A becomes the maximum applied stress. So from there find the AF and then substitute into the equation, right? So you think of all of these things. I had asked you that please don't listen to my solution or don't look into the lecture notes until you have solved it yourself. So now so this is the equation. Therefore, A is 2 into 10 raised to minus 12 and M is equal to 3. They are saying range, it is delta sigma, right? Always remember, sigma R is maximum minus minimum. So I would use the term delta sigma. But what is this? This is not 120 minus 30. It is 120 minus 0. Right? So this is critical. The reason is written here. You see, we have discussed earlier that compressive stresses are good for fatigue because whatever cracks are there, under a compressive stress, the cracks start to close down. So rather than the crack growing, compressive stress is good for us. Only the tensile part of the stress causes the problems. Only the tensile part. So what is the minimum tensile? 0. Maximum tensile is 120 megapascal. So this is very, very critical that the delta sigma is 120 minus 0, not 120 minus 30. That would be a very wrong value. It will not just be a wrong value, it would mean that we are not thinking at all. The upper chamber is totally closed, right? So remember this for always now, that whenever there is a fatigue problem with an existing crack, then the only problem happens under tensile loading, because that is the opening part where the crack starts to open and grows. Under any compressive load, it is good for the crack. So the compressive part you remove from the calculations. So now this is there, that capital A is this, small m is this, delta sigma is this. From the K1 equation, K1 is equal to y sigma root pi A, you have taken A outside, so it is 1 upon pi K1C by sigma max, because y is equal to 1, otherwise y is there but y is equal to 1. So of course now K1C value, you put the K1C value, you put the maximum sigma, maximum, because under maximum tensile load will be the critical condition. So you find out and you do the calculation, because it was in megapascal, therefore I don't need to go to the basic units. I know that megapascal are directly cancelled out. So I found it to be 0.0449 meter. Your value may be slightly different. Remember that keep the values till at least 3 or 4 decimal places. Now the NF equation, AF raised to 1 minus m by 2, A naught raised to 1 minus m by 2, A delta sigma, not sigma, delta sigma raised to m, pi raised to m by 2, y raised to m, 1 minus m by 2. right? So now put the value of AF, put the value of A naught which was given, AF you have just calculated, A naught was given, right? And now everything is in meters and so on. A value from here, sigma, it is actually delta sigma, delta sigma. Don't confuse, this is not the maximum stress this time, right? It is coming out to be that because this was maximum tensile and minimum tensile was 0, so it is 120 minus 0. But suppose it was a cyclic load from 20 megapascal tensile to 120 megapascal tensile. So both were tensile. So then delta sigma will be 120 minus 20, right? So don't write sigma here, write delta sigma. In our case, delta sigma and sigma max are the same. So this is the 120 and the rest of the values. Then solve it. I keep on telling you in all of my classes that you should be very good in the use of your calculator. You should know in your calculator how do I do powers, how do I do this. Even in your calculator sometimes you can do differential things and integral things and so on, and you can do statistical calculations. So you should be very comfortable so that you don't have to write too many steps, you can directly do it. But this, after all the solution, comes out to be roughly 2.79 into 10 raised to 6 cycles, right? So this is 2.79 million cycles. So even with the existing crack size, which is pretty big, this is 1 millimeter. 1 millimeter is very visible. So even with this, you still have 2.79 million cycles of life remaining. And right. So you see, this is just one question, just one example. But how do you apply the equation to find the life? How do you find the AF, right? And what do you use in AF? You use the maximum tensile load in AF. What do you use in delta sigma? You use only the tensile part of the load. Then how do you do the calculations and so forth, and right? So if the equation is directly given, it is okay. But even if it is not given, even if you know the first two equations, the K1 equation and the DADN equation, then you can take 2-3-4 minutes and you can derive the NF equation. It is not a complicated derivation. But if the equation is given, then of course. For you, it is open book, open notes. You should not consult with the internet. You should not talk to your friends and so on during any quiz and so on. Of course, it is a matter of honor with you, that this is my honor and I am there in front of Allah Ta'ala. He is seeing me all the time, and the two angels on my left and right shoulders are recording everything. So honesty and so on, and your character is there. But the book you can open, the lecture notes you can open, so the equations are there. The only thing is that do you really understand it? So as I was saying, even this one problem, if you really understand it and you have made all the correct decisions yourself, or you made wrong decisions and now you understand that no, I am not using sigma max here, I am using delta sigma, and in delta sigma I am not using the compressive part, you have corrected yourself, then you are okay. Now you can practice with other problems and so forth, but even if you don't practice a lot, then you are still okay. Also remember that in your book, chapter 13 of the book Anderson is a book only of practice problems, and in Callister or in any other material science book, the chapter where they discuss fatigue and fatigue related fracture, there also you will get some examples. So we are solving some for you here. Chapter 13 in the Anderson fracture mechanics book has more problems that you can solve, and chapter on fatigue and fracture of any material science book can also do that for you.